Okay, welcome everyone to this week's CDAC webinar. I'm pleased to introduce today's speaker, Michael Hu of the X-ray Science Division and Advanced Photon Source at Argonne. Michael may be well known to many of you for his research and development of nuclear resonance scattering and other synchrotron techniques and their applications to problems in condensed matter physics, material science, biophysics, and of course, high pressure research. Michael received his PhD in physics from Northwestern in 1999. He then joined Argonne as a postdoc and was in the first group of beamline scientists we hired at HPCAT in 2001, helping to launch that program. And he stayed there through 2007. In 2011, Michael was appointed as a physicist in the X-ray Science Division, and there he's continued to develop a variety of new techniques, including Mossbauer techniques that he'll be describing today. So glad to have you give this talk. Welcome.
All right, thank you. Thanks, Russ. Yeah, first of all, I'd like to thank you and your colleagues to organize these talks. Well, at least it keep us somewhat connected through this this past year and more. And also, particularly for me, I learned a lot from these talks. So hopefully today I can share something which will be helpful to you guys. Well, this talk is going to be different than all the other talks. Because I'm not the expert in any of particular specific scientific areas, but it's just my field is in this experimental methodology. It's called a nuclear resonance scattering. So so here you see I'm going to focus on the I don't know. Can you see my cursor? Anyway, yeah. So I'm.
Yeah, it's good.
Yeah. Okay. So I'm going to talk about the Mossbauer probe part, and then as to condensed matter, you are all expert in various fields. You have lots of samples. In of course, this subtitle is kind of obvious. So yeah. Okay. So and then well, this one is as I said, it's a little different. And no, it's focused on the method, but so I'm going to share something. Also, don't worry, it's not anything, hopefully not anything difficult, or it's more like a guided tour. Since we haven't been, visiting places, having tours, the vacation. So this is like this in the nuclear resonance land. I've been there, so I'm going to share some photos and slides with you guys. So, okay, and then the nuclear resonance scattering is no stranger to CDAC community. As we have seen here, these are in the past year already. We have like 4 or 5 talks related or on nuclear resonance topic, right? And then you have subject experts like James, Ryan, Willie, and Brent talk about various things. A lot of on magnetism, as you have seen, and then Brent talk about phonons, which is another big part. And then actually Brent is a great nuclear resonance Mossbauer expert also, and he's a long-time practitioner. And of course, Erjan gave a review talk. So many of the slides later I see is kind of repeat or of the previous talks you have seen. So there are many beamlines actually around the world you can conduct this kind of research using this method. They're all high energy synchrotron, modern synchrotron rings, so-called third generation, and they are APS. One technique, this technique requires one thing, which is the pulsed nature of the source, and then the timing mode, which is critical. And APS is likely have the predominant standard operation mode. And then Petra 3, 2, and then to some extent, ESF and Spernate, they have some timing mode they can use too. And then also you see the high energy photon source in Beijing will be coming online soon in a couple of years. So so there are many sources. So it's like it's quite a prevalent tools you can use. And then talking about these sources, as you already know, many these sources has gone through or going to undergoing upgrades. ESS has already done that, and then they're keeping their timing mode. APS will somehow changes the timing mode a little bit, and then that affects one particular area, but the most part is okay. And Spernate and Petra, they say they are going to keep the timing mode as well. And then the Beijing source is have that timing mode in mind as well. And then as to the and then talking about APS upgrade, I don't know, you guys probably already know that right now, recently they just announced APS start period for the upgrade. It will start in 2 years, April 2023. So we have that left us with 6 full runs. So plan your research accordingly, yes. So I mean, for the other sources, you can go to their website and talk to the beamline side. So here I'm going to talk about at APS, the nuclear acid APS, and later on actually particularly at the sector 30. So here are the we have 5 isotopes we study, and then at the 3 beam lines and plus a MOSFET lab. So these are the people, sort of the MOSFET people or nuclear resonance people at APS. And then these are the contacts for the contacts people. We work pretty much together, in collaboration and all that. But these are the contacts for various beam lines. And then okay, so they have we have this website. It's have some information in the development. Actually, about these other beam lines, we have on this link we have like a conference for the conference related to nuclear resonance, and then in there through the years we have several actually workshops on nuclear resonance organized by Compress. So that in that there are talks from Yuming, from Jiong, talk about sector 3, sector 16, and so we can find that. But the one caveat though, I just recently find out the links to the actual talk are missing. I mean the web page is there, but I will so something you need to take care of that. They're I don't know, it's due to security reason, but anyway. So at another thing briefly about sector 30. So so sector 30 is it's a relatively newer beam line, built later, in the APS at APS. So it started operation 2008. Even though its design was done with nuclear resonance in mind, but it wasn't done for a couple of years. But starting 2014, early 2014, we started the nuclear resonance program at there. And then now it's a user instrument accepting GUPs. And so due to its its setup, its source characteristics, it's suitable for tin only. And a little bit more about that. So there's some technical details about the source at the facility at the sector 30. It's mainly the beamline is mainly for this HYRIX experiment, which is used for phonon studies, mainly for like dispersion measurement and also general phonon measurement as well. And then one thing want to emphasize is normally I would want to say that it's not much point, but actually this flux, this 4 gigahertz flux is very high compared to it's 1 order of magnitude actually higher than we used to have at sector 3, and it is also compared to the other sources around the world is the highest, so that it enables a lot more tough experiments. So just about that. And then there are a couple of things to do this, to be able to do the experiment. There's some technical, developments need to be done. And one thing is this high resolution monochromator. It's very, well, it is critical. So that these are the sketches of one of them actually used at sector 30. These are 6 crystal. These are the blue block are single crystal silicon, a very high purity. So that enables to do this, 10 to the 8 energy monochromatization. So, and then here is what it looks like in reality. So you see these, this 1, 2, and then 3, 4 is inside this aluminum box. It's a cryo box under low temperature, so that it limits thermal expansion. And then the last 2 monochromator crystal. So it's and then we try to keep it in the enclosure to control its temperature. The best, of course, is inside vacuum, but that's have other issues, technical and budgetary. So this is as much as we can do, because we're talking about 10 to the 8 energy resolution. So it's very sensitive to even the light in the room and things like that. And then we have this beam pipe, even though it's 24 keV for tin, we still need to, it's a long station, so we need some to limit absorption. So here is familiar to many of you. This is a KB mirror to focus beam, and then see there's a DAC, and then there's a forward detector here, APD, to do the nucleophile scattering, as we will explain a little bit later, and then to look in detail about the sample. So this is a DAC, and then these 3 aluminum box are APD detectors. They are fast timing detectors, which is another critical piece of this this method. So, and then this is just like a sort of random list of what mostly is done at sector 30 with the tin resonance. So as you can see, they are spanning many areas, many kind of material forms, films, nanoparticles, and then all kinds of from molecular material to solids. So and then under pressure, of course. And then these 2 plots, you see the one on top is the typical forward nuclear resonance forward scattering spectrum. They are time spectrum, so the x-axis is time. So you see, watch it how it decays. And then the bottom is the phonon that just stays derived from the measurement. So in this case, actually, it's tin iodide. It goes through pressure amorphization under pressure, and then recrystallize later. So anyway, this is just some examples, to show you the expense, the things you can do with this. Okay, so now we're going to talk a little bit more about this most-bar isotope probes. So you know isotopes, and then there are particular subset of isotopes which are how to say can be utilized to probe solids and materials we're interested in, right? So talking about probes, I think we're all very familiar with kind of external probes. So basically, X-rays, because of synchrotron now is very popular, neutrons, and also you're very familiar, lasers, light, radiation, fields, and all that. And then basically, many particles, elementary or not. You can use them like in the, you send in, a beam of these particles and then see how it changes direction, how it changes energy, or even actually when it's see how much get out of the sample is also can tell you a lot about the sample, about the properties. But there's another kind of a probe, which is probe, I guess, in the common daily life sense. It's some gadget, right? You send into somewhere or someplace, and then it has its internal structure or internal mechanism, internal state, and then that will change to the surrounding. And then for the daily life, daily life, it listens to our instructions and then let us know. For example, we all know now it's very famous, Voyager, the spacecraft, the probes on Mars now. There are several of them. Anyway. So, but here I think the anthropomorphizing can go only as far, because the probe we're talking about cannot take our instructions and let us know, but they are similarly. What I can do is actually we somehow excite those, and then watch its behavior afterwards, and then that way we kind of send instructions and then measure output. And then talk about internal probe for materials or matters we're interested in. These days everything is microscopic, atomistic, right? So what can be internal to that? I mean, electrons are small, atoms are small, but they are actually most times the problem themselves, right? So but nucleus is very interesting or distinct in that sense. Is actually nucleus itself is not affected by the stuff we're interested in on these energy scales, right? So nuclear property, you can say, is undisturbed, so that it's very well characterized probe. So that's why that's what we can use. So the technique use these internal probes. Besides nuclear resonance, another thing is I can think of is this NMR, nuclear magnetic resonance. That's also used nuclear spin to do these things. And another thing, kind of internal probe, is your rubies, your ruby particles. It's kind of you put inside a sample. But really think about it, it's not really inside your sample, it's near your sample. But anyway, that's something similar too. So so talking about a nucleus, because nucleus has a well-defined property, well-known, and it has this mass, which is important because we know all the mass really is reside on the nucleus. And then the phonons, talk about the motion of the internal motion, vibration of the material, that's mostly on nucleus. And then there are things to study, so-called phonons. For example, neutrons directly probing nucleus. Nuclear resonance is also, but things like we mentioned at sector 30, there's another technique, HERIX, which is inelastic higher energy resolution inelastic scattering. That's study phonon, but actually that scatters off electrons. Of course, with Oppenheimer approximation and adiabatic approximation, it's okay, but still you need to be. But anyway, that's very. But saying that this give us a handle probe motions, atomic motions, and then it has a size which is relevant and useful later on. We will see so-called this thing Isothermal shift we can measure, and then it has charge is also part of that. But more importantly, it has a charge distribution because nucleus has finite size. There's nuclear physics and all that determines, and then it has this thing called a quadrupole. It has electric quadrupole, and then you measure that, it give you information, which is the electric field gradient. And then spin, you well know from the previous talks. I mean, using the spin, you study magnetism, of the sample. Basically, you measure the magnetic field, and then these nuclear levels are very well defined. because the nuclear levels we're talking about is keV, but their energy width is nano eV or on that order. So you can think of it as a very high quality resonator. So because of this, it can preserve coherence. And then that's just another big, factor in a lot of these techniques. This is the principle of it. And then that's why actually these related, the nuclear resonance, the most part field has a lot of physics in it. Actually, it's quantum physics in it. And so coherence is a big part. And then other nuclear properties, of course. So again, just briefly run through, at this point, probably some of you are familiar with this. So this is an isothermal shift. So we're talking about, you see here, these are nuclear, this is the nuclear charge, and then this is nuclear size, okay? And then this phi, this psi is the electron density at the nucleus. That's at zero, because on the atomic level, on the atomic length scale, nucleus is really just a point. And then actually both ground states of nucleus and excited states has a certain size, and then if size changes, and there are shifts in this energy. So that's the so-called, it's related isothermal shift. Actually, isothermal shift itself, it means relative, because this is the both level shift. We don't really know just looking at itself. So you have to compare with something else to measure this shift relative to others. So and also particle splitting, because nuclear has the spin, and then it has this this quadruple, and then it will again, you see this nice separation between internal property like this spin and the charge versus the external, which is this the V is the electric field gradient, again at the nucleus, basically at one point, and then it's parameters 2 meter, because it basically is tensor, and then there's a principal axis, principal component, as well as asymmetry parameter, this eta. So, and then this magnet, it's called hyperfine interaction, magnetic splitting, magnetic level splitting. So this is it's well known. It's clearly and then you see the expression a little bit similar. It's just proportional to the magnetic field experienced at the nucleus, and then with magnetic moment, nuclear magnetic moment. These parameters, nuclear parameters, are well known, so we can use it, right? And then again, probably at this point, tired of it. You see it many times already. This is putting everything together. So you have this these isomer shift, and then you have this epsilon quadruple splitting, and then again, and also the magnetic input. So this is all these levels. So you can see all these terms, splitting, is talking about in the energy domain term. So basically, when you do most part spectroscopy, and you see these different energy lines, right? But in the forward scattering, in the synchrotron case, it's it's in time domain, so it's a little bit complicated. But it's still physics is the same. We still use the name, all these things. Okay, so now those are almost like not quite isolated nucleus, but pretty much there's a single nuclear property. But we know in solid there's something more, right? Because in solid, so that's actually is the thing leading to Mossbar's discovery. So in solid, what these transitions will be affected by. So again, the nuclear excitation has these are keV. This is our low nuclear excitations. So but anyway, and then we know these nucleus are involved in vibrations, and then these yellow bands are so-called phonons. And then as I say, if we don't change, no energy exchange between the incident beam and the lattice system and the nucleus, you have this so-called elastic line. And actually, that's where all the conventional MOSFET, the nucleophile scattering happens. But you can also, for example, the blue lines, you can also, take it's already take the energy of the phonon system and then add it to the outside energy coming in. You can still make up to the okay. So what it means is you annihilate a phonon and then still excite nucleus. So you still have signal. So these are the energy scan. If you tune your energy here's the importance of the tunable monochromators. So you tune the energy away from the resonance proper. You can still excite nucleus. So nuclear levels, right? So this is called phonon excitation density spectrum. So anyway, this is the principal foundations of the phonon measurement, and this is only made possible with synchrotron. So hence this study 90s. This is the one of the important techniques used in nuclear resonance. So again, talking about isotopes, there are a few isotopes which has this kind of a low level and then has enough cross section. You can excite them and then study. And many of them are studied by conventional MOSFET. So you need a source to excite the nucleus, and then. But with the synchrotron, our synchrotron is the source. But then there's technical difficulties. So not all of them are studied or can be studied by synchrotron at current moment. As you see in the previous slide, for example, at the APS, we have 5 isotopes, right? And then at ERSF, and then Petra 3, and then Spring 8, they have a few more. So here I have to talk about MOSFET. So well, so one thing, he's these we all know he got a Nobel Prize, but that work, that research was his PhD thesis actually. And then fortunately for us, he well, how to say, let's step back. He was doing nuclear physics, and then he's trying to do this resonance absorption, and he finds something puzzling. The reason is, even though, as you see from the date, it's 30 years later and 30 years after quantum physics, quantum mechanics has been established, but still, in terms of solids, it's not well understood, and so he was puzzled. And then, but unfortunately for us, he didn't give up. He didn't just, how to say, put it on the rocks, right? So he spent a year or so. He tried to figure that out, and then it turned out to be this is actually a quantum effect. This is quantum physics, and so he got a prize. And then at that time, actually argon. I mean, you're from Urgent's talk, you already know argon is the one of the places which there are several people started this MOSFET business, intensely. So there's works at the lab and all that, and then also so it's naturally we have a nuclear resonance beamline at the there. Okay, so this resonance absorption, it's also another thing I actually didn't mention is actually this coherence, and that actually is the enhancements to make many things, make this so-called congruent possible. I mean the effect is the MOSFET effect. The gist of the MOSFET effect actually is recoilless absorption or emission of the X-rays or gamma rays. So as you have seen the pictures a little bit already, you see the pictures of the monochromator, the APDs. So this is what we do. and then this that's two parts of the experiment. One is the forward scattering. There, all you need to do is to allow photon in and then photon out. So your detector can be far away, and then you can now you can see is with this setup, just forward scattering, you can put a lot around your sample. So the sample environment can be very rich. So a lot can be done. There's not much restriction. But for the inelastic scattering, the name of the game there actually is to a solid angle, because the inelastic scattering is an incoherent process, and it's isotropic also. So you want to collect as much as possible, so that the detector need to be close to the sample. That have certain restrictions. So for that, you see the DAC, you saw this panoramic cells. It was developed for this type of experiment, and then there's other cross standards, so it has to be specific for that. And then again, we mentioned briefly that the technologically, there's several requirements. And then the monochromator, the APD, and timings is important, but also the timing structure, because here is what detector sees. For example, the EPS particular mode is this hybrid mode. So you have this prompt, we call it prompt coming in. That's every 3.6 microseconds in that mode. And then everything pretty much decays fast, because all the electronic process is fast. They decays, they are died out. And then, but nuclear still decaying and have longer on this scale, longer lifetime. So you see, so these are our signals. So from this point, you can see it has intrinsically low background. In theory, it's no background, right? But of course, there's electronic noise, there's cosmic rays, and all that. And then to achieve a high, signal to noise ratio, I mean, noise we have some control, but the signal is also. That's why we always ask you, whoever comes to the experiment, to put as much, the nuclear resonance isotope, the most isotope in there as much as possible to increase the signal. And then, okay, so what the nuclear forward scattering, this time spectrum can probe, right? So we're going to talk about through isothermal shift, you can study this basically electron density at the nucleus. And then it has to be different. You have to take reference. For example, it shows in this graph. So you measure some sample by itself, you see some time behavior. But in order to measure isothermal shift, you have to put a reference. So you see we have like some oxides. It has a well-defined line, so you can basically put another line in, so you get a kind of beating to measure the difference. And then crossover splitting actually measure the electric field gradient. Again, just it's what we measure. And then hyperfine field, magnetic hyperfine splitting, that's obvious. So talked a lot. Another deal over here is about this forward scattering or this most bar spectroscopy can give you oxidation state, valence state. That is kind of a heuristic, because if you list these isothermal shifts or crossover splitting of many samples, you see them clustering around certain number. And particularly also, if you plot crossover splitting against isothermal shift, you see on the plot it's clustering around certain. And then you can label the clusters with so-called valence state, +2, +3, kinds. But again, this is much like actually the AI, the deep learning now, right? So you have some data coming in and you label them, and then that tells you. But really, what do we measure? The physical quantity we measure, are showing here. So there's a lot of things. You guys are interested in, for example, the acid electron density, the field gradient. For example, you have some distortion, asymmetry in a crystal that will show up. So that's really what we measure. And then also another thing, because again, coming back to magnetic field measurement, using Meissner effect, we can measure this some typos, sorry, superconducting transitions. So that because this is, as we said, the probe and then the detector is far away from your sample, right? So there's I don't know much, but to really measure magnetic field, there's a lot of circuitry around from other ways, and then this is a clear, neat way to measure that. And then the other technique, which involves phonons, these we can measure. So here we show the typical, energy spectral measure. This is the phonon excitation density function, right? To see in the middle, there's a huge elastic peak. That's the exactly on a resonance, and then below and higher, there's also a nuclear resonance happening, and that tells you the phonon involvement, and hence the dynamics, the vibration of the nucleus, and hence the atom, right? And then from there you can deduce the phonon density states, and this PP means a partial and a projected. So the partial is because this technique is seeing the nuclear isotope only, not any iron atom. A particular iron atom has the iron 57 nucleus. So it's partial in that sense, and it also is projected along the photon direction, incoming photon direction. So if you have a single crystal, you have some texture that will show up, and then from these measurements, from these particular from density states, you can measure sound velocity. So that's another great probe. So I will talk about a little bit more. And then, of course, this lattice thermodynamics. Once you have density states, that's pretty much all you know. All you want to know about this system. So we can, there's all kinds of thermodynamic quantities. But again, this is only the phonon, and then also the sublattice of iron atoms. And then also you can probe lattice harmonicity, which is basically can probe the potential, the atomic potential experienced by these isotopes. So another thing is this scattering function. It has this thing called a detail balance, so that basically the high energy, the energy plus and energy minus side are related to the Boltzmann effect. So from that you can measure temperature. Well, I wouldn't use it to measure temperature because it's not a precise measurement, because there's a lot of noise in the system, in the signal, unless you measure to super high, complete, which is not practical. But it's a useful indication, particularly in many situations when you're heating or cooling, you don't really know the temperature, and this will tell you. So it's useful. And then again, talking about list a little bit some details about the quantities you can derive from this measurement. All these things, this F factor. If you're a little bit familiar with most part spectroscopy, this F factor, this recoil fraction is an important thing. And then there's many. In the old times, just from the conventional most-part spectrum, you can derive this F factor, but that is that's how to say that is based on a strong assumption. But these nuclear resonance inelastic measurement gives you actually it's an exact that number, so it's a good measurement. So sometimes we even use that just to get an F factor. But it's kind of expensive way. But if you have no other way, that's the way to go, right? And then things like mean square displacement, this is useful. We need to talk about later. And then kinetic energy and all that. And then various force constant related to the potential, but also one of them. This is a moment. The moment of the spectrum is somewhat. It's the force constant, but there's some detail later. And then, of course, many people are measure density states because they want to know a particular vibration mode at what energy, right? And then you can identify which particle and which atom connected to the iron or tin or it's moving. Oh, so that's very useful. And then again, this harmonic term we can talk about a little bit later. And then thermodynamic with all these quantities. And then I guess of interest here is like a Green-Larson parameter, isotope fractionation can all be derived of it. So again, this is partial projected. Partial means iron only. The nuclear resonance isotope sublattice only, and projected is along the. So that only matters if you have a single crystal and all that. But for a powder or isotropic case, it's average out. You get one number out. So again, velocity probe. So this is well known. I think in the high pressure community, the first well-known case is Dave Mao came to our beamline and measured iron up to I forgot now. So over 1 gigapascal. No, over 1 megabar, right? So that started actually the high pressure at the APS, high pressure at the nuclear resonance at the APS. So again, if you get this denser states, the low temperature part is most of the solid is the bilight. So basically, is this quadratic dependence. So from that you can derive this the so-called velocity. And then in case of the bivelocity, and then see here is the velocity of each each dispersion, each branch of phonons, and then this theoretically this is this average, but in many cases you can approximate or into something simple, and then you relate it to, for example, with a little bit more information from other ways for bulk modulus and all that. Actually, you can, from this one, you can figure out what's the transverse velocity and the longitudinal velocity. I guess in seismic wave, that's important. So this plot is the linear behavior. Oh, you see this is over E squared, so the bi behavior. So actually, this whole paper, the whole point of it is this factor. This is important. This tilde is the nuclear mass. Is the for example, the mass of iron 57, and this m, the little m, is the mean weight or mean mass of your molecule of your unit cell. So this ratio. So you can see from this formula, you can already see this low temperature behavior doesn't depend on a lot of details of your dynamics, which means whatever sample doesn't really matter. So you can if you just measure the whole spectrum, properly normalize it, and then get the low temperature part, you can derive a velocity of the solid. The reason is sound wave is a long wavelength. Right, so it doesn't matter what you have here. It's almost like a continuous median. It's not really, but it's kind of like that. So hence exactly the meaning of probe. I mean, one thing is a lot has been done, particularly in high pressure community. We always measure velocity, but most sample measured are with iron as part of your sample intrinsically. I mean, there's a fraction of iron in there. Some, I don't know, minerals, either end member or some intermediate, intermediary. So you have irons in there already. So you measure it, you get a sound velocity. But I think a lot can be done. Actually, go beyond that. You dope certain isotope into it. Of course, you want to make sure it doesn't react, it doesn't change your structure, doesn't change your phase and all that. But I think with that logic, because with the improvement of flux and then detection efficiency and all of that, actually we can measure quite low concentration. For example, this tin platinum, so we only have 1% of tin, and of course it's enriched. It's just one enriched in the particular isotope. Of course, inside the DAC is a little challenge because there's already not a lot of material, right? But I'm saying it can be done. So, oops, what happened there? Okay, so that's about use it as a velocity probe. And then also not just velocity, actually is related to the elastic properties, right? So I think there's a lot of interest there. So, and then another thing is harmonicity probe. I'd like to talk a little bit more about. I mean, the details is in the paper, but again, if you do this, measure the spectrum and then calculate its moment. This is the third moment of measured spectrum. And then it's related to the the potential through this equation. So the K is the so-called mean force constant. That is harmonic. If you have harmonic lattice, harmonic potential, that's the only term you have. So that's the force constant. But in reality, of course not, right? So we have a complicated force, complicated potential. And then at least, this is the next term, which we can see. The thing is, we don't really see the other term. For example, cubic term is actually most often in aharmonic material, but we don't see it. But we do see this quartic term. And another thing, sort of a caveat is there's no one atomic potential at all temperature and pressure, right? Because we know that at any particular, at a different temperature or different pressure, the lattice is different. So the interaction, in many cases, will be different. So you have actually different potential. But if the change in pressure or temperature is not a lot, so that would be a good approximation. So that's why I say this is a kind of a local approximation. So as an example, why I keep doing this? Wrong key. Okay, so as an example, this is the sigma phase of iron chromium alloy, and then at the low temperature, it goes through a magnetic transition, and then if you plot these this so-called force constants or third moment, and then versus the mean square displacement, which you can get from the F factor as well. So both x's are measured quantities, and then you plot them, and you get this. So clearly, it tells you this is unharmonic, because in harmonic situation, you will have a straight line, right? Because the force constant, the potential doesn't change with the vibration or displacement. But now you do, and then you see the first part, this lower temperature part. Actually, the B term, that the linear term, is negative. Negative means in the potential you have a negative quartic term. Quartic term is kind of large, right? So you can almost say it's unstable, because you almost have a negative potential. Maybe you just like a local minimum or something, but there's negative potential around it, so it's unstable. And then the other part is more well, anyway, it's positive, so you have a deep potential well. But anyway, so this is what you can extract from the measurement and to tell you something about your system. So so I think that's about it. So I will just show you this most of our isotope is yeah, of course the cool probe, that part is my bias, but nonetheless I think it's very useful. And and then nuclear resonance is there's a lot can be done. A lot already has been done because this starting in the early 90s, the elastic technique has been used. So a lot has been done, but still there are a lot more can be done also. And then to explore, because if you have your materials, if you have some properties you want to measure, you are interested in, and also there's some physics in there, and also particularly you see we measure a lot of quantities, right? So if you can do simulation, for example, to simulate the phonons or calculate this electric field gradient, the electron density or the magnetic field, obviously. And then the thing is from what I see at the beamline is we measure a lot of stuff, but we need someone to how to say, maybe to make better sense of it. So you need to some simulation, some modeling. So that's highly wanted. And then in that context, out of those many things we can do, I picked those kind of three things. I think it's of particular interest and can be extended a lot. The sound velocity, really, use this idea of a probe, not just part of the system, of a probe, and then the first of all the seismology, of course, but also the elastic properties of material, and also lattice harmonicity is also very interesting, because that's the real material. It's a lot of physics in there, and of course the superconducting transition is I think it's a very neat way to indicate that. Hopefully that will make that identification much easier, so you can go to all kinds of conditions and all that. So with that, I like to thank you.
Okay, thank you, Michael, for the nice review of the technique. I'm pleased to see the way you complemented the previous talks in our series using nuclear resonance techniques, Mossbauer techniques. So thanks very much. The talk is open for questions and comments. I guess we have a couple already in the chat box. Winley, do you want to speak up?
Hi, Michael.
Hello.
Good to
Hi,
see you.
Winnie.
Hi, I'm in the lab, so I have to wear masks. So you mentioned to get the phonon density state, if you have isotope that is Mossbauer active, you just get the partial phonon density state, and you have the m tilde over m. Could you even elaborate how to get the total phonon density state if you have, let's say you have in the system you have two elements, and both elements have isotope, Mossbauer active isotopes. So if we get the partial density phonon state from the individual isotope, from there, how do we get the full phonon density state?
Okay. Well, thanks a lot. Good question. Actually, that has been done already with iron dysprosium compound, I think, because both iron and dysprosium are Mossbauer active, right? So it's been done, it's measured. So there it's simple. It's very simple. You measure iron, and then you measure dysprosium, and then you just add them up. Of course, the normalization, because normally, from the program, we normalize everything into 1 or 3,000, whatever. But really, it's it's not that. It's partial, right? But you have to take a proper proportion, because from your chemical formula, that, and then you just property partition them and just add them up. You got total density state.
Do you consider the other isotopes, non-Mossbauer active isotopes, in the element?
No, if you do have a non-Mossbauer isotope in there, then we can't see it. We can't see it. So that's why actually the simulation is important, because certainly you can simulate those, and then
So you use M2 over M, and M actually is the average mass of all the atoms, right?
That's right.
So that include the non-multiply active.
Oh yeah, yes, yes, yes. That's right. That's right. Actually, I don't know. As some of you may know, actually, the story of the paper is people realize you need to know. Okay, this is the biobehavior, right? Okay, so that's just that. And then I noticed, there's some inconsistency there. There's a normalization issue, as I mentioned already. So that's why we figure out this is has that factor in there. And then that way you have a correct, velocity because you measure this, you normalize, that's fine, and then of course without this factor, it's obvious this V what you get out is wrong, right? It's wrong factor. So actually that's the whole point of the paper is to prove it is the case, and yeah. So that's again coming back to you have because as far as this long wavelength dynamics is concerned, it doesn't matter what's in there, and then the iron, the nuclear, the resonance isotope participate in that long wavelength motion, and that will tell you the velocity.
Okay, thanks. I'll go into that paper in more detail.
Okay, thanks very much. Brent, do you have a question?
Oh,
sure, I can ask one. I can also comment on what Wenli B just asked. If you have another technique, such as neutron scattering, you have the same problem where the different isotopes have different scattering weights. But then if it's an iron alloy with something else, binary alloy, you can sort out the two partial densities of states for the iron and the other element by comparing the neutron to the iron 57 nuclear resonance scattering. But you have to have the same resolution for these two, so there's another issue with that. But anyway, you were quite right about the long wavelength limit, though, Michael. That's very true. I was wondering about the issues with these shorter-lived isotopes like europium and dysprosium, where we aren't so successful at the advanced photon source because of the bunch purity problem. I think ESRF has a little better control over that, and you don't need to veto quite as many pulses for the first part of the time spectrum. Is there anything that can be done now to argue for or design or plan better bunch purity after the upgrade of the APS?
Well, it's a long struggle. It's a long-term struggle. This since the beginning of APS, because due to the setup of the APS, because it has a positron accumulator ring, and then it has the booster ring. There's some kind of timing mismatch. So our problem is we have a high impurity bunch at the third bucket, and then that's already a 9 nanosecond.
Yeah. Right.
So yeah, we've been through years talk to them, and then they this is let's say this is an ongoing discussion, and yeah, it is quite a hindrance to us because even for teen, I mean we cut out a lot, almost a full lifetime already. So that is an issue. I mean our APDs are okay, and then so in terms they can get close to whatever it is, but if you have such a high signal, yeah. So no satisfying answer to you.
But I mean, is there a way to phrase this as an exciting design challenge to the machine designers for the upcoming APS modification, the upgrade?
I do have a guy. Well, he was a kind of new accelerator guy, and he came down to my office, and I asked, okay, what are, and then it's just that. just.
All right, good luck.
But
Thanks.
yeah, well, yeah, but I think yeah, I don't know for the other, if we can get some other timing people, if they are care about, but I don't see that, because see, our signal to noise ratio is oh, how to say that? So our prompt is and versus our signal is 10 to the 8. We're sensitive to that level, right? And then they're saying, oh, we guarantee purity at the 10 to the 6. That's not good enough for us. But for a lot of other people, I mean, 10 to the 6 is pretty good, right? So.
Well, with the delay in the upgrade, maybe there is some room for design changes.
yeah, well, but I don't know. They're just busy and get everything done, I guess. But.
Okay, more questions or comments? Maybe coming back to that first question, since you have the slide up here, I can't remember in this paper, which I read many years ago, in the first case, you have tin doped into palladium. And so when you vary the concentration of tin in palladium, do you see any systematics for how you would extract a more proper or more exact velocity, temperature? Because it's a very different case than the ones below, where you basically have a dopant in the structure, as opposed to your component.
Right, exactly. If I remember, I think we also have a sample with 5%. I don't remember if it's put in the paper or not, but I think we get a similar result. And then, but that's just room temperature, just bulk sample, a chunk of sample measurement. We didn't really, because I guess it's not really that interesting in the palladium, sound velocity. In principle, yeah. So that's the thing. You do a temperature dependent, measurement, or you can find out more. But and then, oh, sorry.
Yeah. Okay. I was just going to ask. You mentioned temperature. What's the maximum temperature study so far using various nuclear resonance techniques? Not necessarily under high pressure, but perhaps under high pressure. Heating and so on.
I think once we did some glass measurement, use a furnace, it's go up to, I don't know, I guess below 2000 K, but over 1000 for sure. It's not melting yet, right? It's not melted yet.
Well, I was wondering about that in the case of, actually crossing a melt transition. So looking at liquids, has that been explored much?
No, because once it's going through liquid, you see the thing happens. The most of our part becomes becomes an issue, because then there's no recoilless recoilless absorption anymore. So you will get a broadened elastic peak, and then it's quasi-elastic then. And then there's all kinds of diffusion phenomena coming in, but how to say? So I'm glad you mentioned this, because now there's another development in the nuclear resonance. It's called nuclear resonance time domain interferometry. That one, I didn't talk about that because first of all, it's a new development. It's in the past couple of years at most. And then, but it's not an internal probe, because for that study, you don't need isotope in the sample. What you do is you set up your beam with a nuclear resonance. Some beam, get set up this timing pattern, and then it goes to your sample and then scatter out. And then you use some kind of a resonance sample to analyze that. So your sample is completely free of isotope. You can, of course, it doesn't hurt in there too, but anyway. And then there, people mostly study is the liquid dynamics, the diffusions and all that. So of course, there you probe the type of the dynamics on the nanoseconds time scale. So that's actually a great development. And then with that, again, a lot more can be done.
Okay, thanks. More questions? If not, thank you very much, Michael, for a very nice overview.
Right. Well, thank you, everyone. Thank you.
And we'll see you next week.
All right, bye, Russ.